So this idea of proof, we've seen some different types of proofs. Probably the most common type of proof that we have done is deductive proof, and most commonly seen with geometry. So that's when we start with known facts, and so in geometry it's our geometry theorems, and then from those facts we deduce what it is we're trying to prove. Then of course we saw inductive proofs. So that's where we actually assume what we're trying to prove and then induce the solution. You may not remember it, but last year we also looked at one, proof by contradiction, where in that one we actually assume the opposite of what we're trying to prove. And then, assuming that to be true, we come up with a contradiction. And so because it contradicts, that then leads you to the conclusion, well, if this is a contradiction, then what I originally assumed must be false. And so then you go back to the opposite being true. All right, so they're the main types of proofs. So in our inequality, some techniques that we often use to solve these problems. Now, if you have to prove x is greater than or equal to y, a lot of times it's actually easier to prove x minus y is greater than or equal to 0. So show something is always positive, or something is always negative if it's a less than or equal to. Because once you've proven x minus y is greater than or equal to 0, that becomes a fact, so then you can move the y to the other side and you can conclude, oh well, x is greater than or equal to y. So going back a very long time, but it is quite a common little question, this one. Prove pq is less than or equal to p squared plus q squared on 2. So rather than doing that, I'm going to play around with p squared plus q squared on 2 minus pq. Notice I haven't put an inequality sign there. I've simply got an algebraic statement. I want to show this algebraic statement is always positive or always negative. What do I want for this one? I want to show it's always positive. So let's create the fraction, and it comes out quite easily, because you'll see on the top of the fraction, we've got our perfect square. So we end up with p minus q all squared, which is always greater than or equal to 0. So I now know that my piece of algebra is always positive. That's now a fact, so I can then play around with it and say, oh well, therefore p squared plus q squared on 2 is greater than or equal to pq. Well, technically it's written the other way around to what they asked to be proven, but obviously it's the same thing. Okay, now had I done this by contradiction, again, I'm not suggesting you'd use this method, but let's do it by contradiction and say, no, we're going to assume PQ is actually bigger than P squared plus Q squared on 2. Well, if that's true, because remember, I'm assuming this to be a fact, so I can play around with this. So 2PQ then would be greater than P squared plus Q squared, which means 0 is going to be bigger than p squared minus 2pq plus q squared. 0 is going to be bigger than p minus q squared. Well, that of course is impossible, because p minus q squared has to be positive. So we know it has to be positive, so there's my contradiction. So my original assumption must have been wrong. So if pq is not bigger than p squared plus q squared on 2, then it must be less than or equal to p squared plus q squared on 2. So I say that's how I would do it using proof by contradiction. It's probably not a common way of doing that particular type of problem, but you know, it works. Let's have a look at one that's more fun. Prove that a squared plus b squared plus c squared is always greater than ab plus bc plus ac. Now what I tend to do with this sort of one, and the other idea is start with a known fact. I know a minus b squared is greater than 0, because if I've got a known fact, I can play around with it and come up with a statement. So therefore, a squared minus 2ab plus b squared is always greater than 0. So I know a squared plus b squared is greater than 2ab. But of course, a and b are just pronumerals. I could have put any letters there. So it must also be true that a squared plus c squared is greater than 2ac. B squared plus c squared is always greater than 2bc. If I add all three of those up, I get 2a squared plus 2b squared plus 2c squared is greater than 2ab plus 2ac plus 2bc. So all I've got to do is divide by 2 and I have my result. Okay. So that idea of starting with a known fact And again, it's coming up with that idea of something's always positive or something's always negative. Well, in that case, it's still part of the same question. If A plus B plus C is actually equal to 1, let's prove that AB plus AC plus BC is less than a third. Okay. Well, A squared plus B squared plus C squared, we know is going to be A plus B plus C all squared minus 2 times the product. Okay. So I could rewrite the result that we just proved. Instead of saying A squared plus B squared plus C squared, I could write it as A plus B plus C all squared, which I know to be 1, minus 2AB plus AC plus BC. Well, that therefore means 3 lots of AB plus AC plus BC is less than A plus B plus C all squared. So I've sort of moved the AB's, AC, BC's to the right-hand side, but then I've made it the left-hand side, so that's why the inequality sign's changed around. But as I say, we know A plus B plus C is equal to 1. They told us that. So 3 lots is less than 1, so AB plus AC plus BC is less than 1/3. Then it asked us to prove that 1/3 of A plus B plus C is greater than or equal to the cube root of ABC. Okay, we know A squared plus B squared plus C squared is greater than or equal to AB plus AC plus BC. Okay, I'm going to use the idea, let's move everything to one side, let's play around with it. So all of that has to be greater than or equal to 0. I'm going to multiply both sides by A plus B plus C. Well, if I expand that whole thing out, something lovely happens. There's a whole heap of cancelling there. And I get A cubed plus B cubed plus C cubed minus 3ABC. It's getting very close. So I now know 1/3 of A cubed plus B cubed plus C cubed is greater than or equal to ABC. But remember, A, B and C are just pronumerals. I can substitute anything into that. So I'm going to let A equal A to the power of 1/3 and B equal B to the power of 1/3 and C equal C to the power of 1/3. Well, if I cubed A to the power of 1/3, I get A. If I cube B to the power of 1/3, I get B. If I cube C to the power of 1/3, I get C. And on the right-hand side, now I have A to the power of 1/3, B to the power of 1/3, C to the power of 1/3. Well, hang on. That's the cube root of ABC. My result. Basically, what we're proving there is the arithmetic mean is always greater than or equal to geometric mean. So that was the one for 3 numbers. So all right. Oh, by the way, that idea, arithmetic mean, geometric mean, unless it is, of course, what they're asking you to prove, you can quote it. It's a known result. The arithmetic mean will always be greater than or equal to the geometric mean. All right. This time we're going to suppose that 1 plus x times 1 plus y times 1 plus z is equal to 8. And we're going to prove x, y, z is less than or equal to 1. If I remember correctly, I think I ended up doing this 2 ways. One's quite fun, the other's quite quick. The fun one's not that quick, but gee, it's good. You're going to love it. Watch this. Okay. 1 plus x times 1 plus y times 1 plus z is equal to 8. So, oh geez, what to do? Oh, let's expand the whole thing out. So 1 plus x plus y plus xy plus z plus xz plus yz plus xyz. Now I know, arithmetic mean greater than or equal to geometric mean, that 1/3 of x plus y plus z is greater than or equal to the cube root of xyz. Okay. So another way of saying that is x plus y plus z, which you'll notice we've got on the left-hand side. I've just multiplied both sides by 3. Greater than or equal to 3 lots of the cube root of x, y, z. But of course, x and y and z, I can substitute anything in I like. So for x, I'm substituting in xy. For y, I'm substituting in yz. For z, I'm substituting in xz. Don't think of it as A plus B plus C. Just think of it as 3 things added together will always be greater than or equal to 3 times the cube root of those three things multiplied together. That's all we're saying. Now on the right hand side, xy times yz times xz is x squared, y squared, z squared. So I now have two parts of my left hand side. So xy plus yz plus xz is greater than or equal to 3 times the cube root of xyz all squared. So remember, this was our statement, at 1 plus x plus y plus z. Well, let's substitute in what we've just proven. So I'm replacing x plus y plus z with 3 times the cube root of xyz. And I'm replacing xy, xz, yz with 3 times the cube root of xyz squared. And that now would be less than or equal to 8. You might not recognise it yet, but I'm going to write that last term a different way. Instead of writing it as xyz, I'm going to write it as the cube root of xyz cubed. Because now have a look at the pattern. 1, 3, 3, 1, power of 0, power of 1, power of 2, power of 3. That is 1 plus the cube root of xyz cubed. Wow. Now I'll find the cube root of both sides. So 1 plus the cube root of xyz is less than or equal to 2, which means the cube root of xyz is less than or equal to 1, which means xyz must be less than or equal to 1. And that's what we were trying to prove. So that's the long way of doing, but gee, it's nice, didn't you? Isn't it lovely? You come up with that pattern that we recognise from the binomial theorem and so on. Okay, I'll show you the quick way of doing it. Where's the fun in that? All right, or I could simply do this. Well, 1 plus x will always be greater than or equal to 2 root x. Again, it's arithmetic mean, geometric mean, but this time with two terms. So two terms added together will always be greater than or equal to 2 times the square root of the two things multiplied together. And x times 1 is x. Same with 1 plus y, same with 1 plus z. I could say these are simultaneous equations. But instead of adding, I'm going to multiply. I get 1 plus x times 1 plus y times 1 plus z is greater than or equal to 2 root x times 2 root y times 2 root z, which is 8 root xyz. But hang on, they told me that 1 plus x, 1 plus y, 1 plus z is 8. So 8 is greater than or equal to 8. And it comes out a lot quicker, but nowhere near as much fun, was it? I mean, yeah. So that idea comes up a lot in these inequality questions, using the idea arithmetic mean greater than or equal to geometric mean. Let's try this one. Now we're going to have some fun. So we're going to trap 2 on a plus b plus 2 on b plus c plus 2 on a plus c in between these two expressions. Okay, so I'm going to do it a bit at a time. Notice I'm using again the arithmetic mean, geometric mean idea. And I've started with a plus b times 1 on a plus 1 on b. So the a plus b is greater than or equal to 2 times the square root of ab. The 1 on a plus 1 on b is greater than or equal to 2 on the square root of 1 on ab. Oh, by the way, a and b and c, all these pronumerals are positive numbers. Obviously, if they were negative, this wouldn't work. Okay, but they have to be positive numbers. Well, on the right-hand side, the square roots cancel out and I just get 4. Just get 4. So now if I divide both sides by a plus b, I get 1 on a plus 1 on b is greater than or equal to 4 on a plus b. But remember, a and b are just pronumerals. I could change them to anything I like. So it's also true that 1 on b plus 1 on c is greater than or equal to 4 on b plus c, and 1 on a plus 1 on c is greater than or equal to 4 on a plus c. So if I add them all together, I get 2 on a plus 2 on b plus 2 on c, and you can hopefully notice now that, hey, if I divide everything by 2, I've got the right-hand side that I'm looking for. So I've got the 1 on a plus 1 on b plus 1 on c is greater than or equal to 2 on a plus b, 2 on b plus c, 2 on a plus c. Now, how to get the other side? Well, I'm going to do a similar thing, but this time with all three terms. But I'm still using the arithmetic mean, geometric mean idea. So the a plus b plus c is going to be greater than or equal to 3 times the cube root of a, b, c. And the 1 on a plus 1 on b plus 1 on c, the cube root of 1 on a, b, c. The roots, the cube roots cancel. I get 9 this time. But look what I've got on the left-hand side. 9 over a plus b plus c. That one's quite quick. Hang on though, that's not what we're trying to prove. All I've just proven is the right-hand side is bigger than the left-hand side. I still haven't got that middle term in there, so I'm not quite there. So I'll just do this. A and B and C are just pronumerals. So I'll replace A with A plus B, I'll replace B with B plus C, and I'll replace C with A plus C. Okay? Now I get 1 on A plus B plus 1 on B plus C plus 1 on A plus C is greater than or equal to 9 on 2 lots of A plus B plus C. Well, multiply both sides by 2, I now have the required result. So therefore I've now trapped the 2 on A plus B plus 2 on B plus C plus 2 on A plus C in between those two results. Let's try another one. If A, again, we're usually dealing with positive numbers for these things. So A is greater than 0. We're going to show that A plus 1 on A is greater than or equal to 2. Well, arithmetic mean, geometric mean. Some debate here that, am I actually proving the arithmetic mean, geometric mean? I say no. I say this is just an application of it. So I'm just going to sub straight into that idea. Well, if I add two numbers together, I know it's always going to be greater than or equal to 2 times the square root of two things multiplied together. So we have A plus 1 on A is greater than or equal to 2. Okay. Of course, the other way I could do it, I could have done it like I did when I actually proved the result by saying, hey, I'm going to start with a known result. The square root of A minus 1 on the square root of A squared is always positive. So expand that out and move to the other side and I get the result. So that's another way I could have proven that. Okay. So now, and you're probably looking at it going, oh, it's obvious what we're going to do. B plus C on A plus C plus A on B plus A plus B on C is greater than or equal to 6. We've just proven that A plus 1 on A is greater than or equal to 2. All right, so basically we're saying something plus its reciprocal. So I'm going to go B on A plus A on B is greater than or equal to 2. That also means C on A plus A on C, C on B plus B on C. If I add them all together, I'll get something that's greater than or equal to 6. Have a look at it closely. Group the denominators together. Over the A, I've got B plus C. Over the B, I've got A plus C. And over the C, I've got A plus B. And that's what we were trying to prove. All right, then, let's try this one. A on B plus C plus B on C plus A plus C on A plus B greater than or equal to 3 on 2. Okay, we just proved, hang on, let's go back. We just proved that B plus C on A and so on. So there we are. Be lovely just to turn both sides upside down, but of course we're not allowed to do that. What we do is simple. Replace A with B plus C, replace B with A plus C. So why on earth? I'm just making the denominators the same. So I'm replacing A with the first denominator, B with the second denominator, C with the third denominator. Let's see what happens to the numerators. So I get A plus C plus A plus B, A plus B plus B plus C, B plus C plus A plus C, which is 2A plus 1. So I've got 2A plus B plus C on B plus C, which is 1. The next one, 2B on A plus C, plus 1. 2C on A plus B, plus 1. move the 3 over to the other side, divide by 2, and we have our result. So a heck of a lot of algebraic manipulation involved. All right, now in the handouts, there's an inequality sheet in there, which if I remember correctly has solutions with it as well, which makes it quite good. Obviously there's our Cambridge Patel exercise 10D. Way back in our extension 1 book, Cambridge 8H, but just question 28.